As Molly said, my name's Walter Goody. I'm an applications engineering manager here at Mentor Graphics, and I also support all the front-end functional verification tools for the distribution customers. So today's webinar is about verification performance. First thing we'll do is just have a couple of quick slides about what performance means. Then I'll go into how to tune your performance with the Questa Core or Questa Prime product. Talk a little bit about if you have simulation bottlenecks, how to find and correct those. And then the last section, I'll talk about optimizing your debug. So if you look at, the last couple of decades, way back in the late 90s, there was this concept of the silicon vendors, the FPGA vendors and the ASIC manufacturers. We still have Moore's law. Silicon is doubling in size every 18 months. And the concern in the late 90s was, hey, they are creating these bigger and bigger chips, and are the engineers going to be able to design enough logic to fill up those chips? Well, it turns out that engineers are pretty clever, and we just kind of said, hey, we can take these two FPGAs and integrate them as one. We can put 4 data paths instead of 2, running in parallel. So there was a lot of things, and it was really the fact that the designing of new logic has been kind of going down, and then using either in-house developed logic or getting IP from your FPGA vendor, your ASIC vendor, from third parties has gone up. So it turns out we can fill up those designs pretty easily. But what it's tough to do is to make sure that all that logic operates correctly together. And you can see that looking at the trends. And this is definitely in the ASIC world, that if you looked back a decade ago, there was probably 2 design engineers to every 1 verification engineers. And today, that's probably closer to, we probably have more verification engineers than we do design engineers on any ASIC project. And then if you look at, what is the biggest task as part of your project, it is generally the verification step is probably averages somewhere around 60 or 70% of the time is spent there. And, if we got silly and, just projected the trends that we're seeing, by 2037, you're going to spend all of your time doing verification and none of your time designing. But that's, that trend is probably somewhat true. We keep innovating on the design side of things with, higher level languages, so doing C-based design, all these things, and the verification step continues to be just the thing that takes the most amount of time. So basically, people always say, hey, if I had a faster simulator, I could X, Y, Z. So the first bit we'll do here is just talk about how to make sure you really have your fastest simulation environments. And so a couple of tips that I like to give is, I don't know how many of you do VHDL designs versus Verilog designs, but if you do use the VHDL designs and you do use the math packages, the standard arith package, the standard math package, the standard, etc., signed and unsigned packages, just make sure that you're referencing the official IEEE versions and not kind of the legacy Synopsys ones, because we've spent a bit of time optimizing those official IEEE ones. Here's one that I think is really important. when you're doing your simulation, if you have upgraded from ModelSim or Questa, 10 dot, whatever, and you've upgraded to the latest one, which this year we went to a new naming convention. So we have, 2019.3 is the current release. So we're doing quarterly releases. If you've upgraded your tool, make sure you upgrade the ModelSim INI to match that tool. Just because with some of the new technologies, we put some arguments in there to make sure it's running the fastest. And if you're using an older ModelSim INI, you may not be taking full advantage of the new simulator. This last one, I almost am not. I'm probably going to delete this off of the thing. I used to tell people use the 32-bit version of Questa unless they have a really big design, just because it's a little bit bigger memory footprint and a little less performance. But I think we've pretty much closed that gap. And actually, I think in the next year or two, we're probably going to discontinue those 32-bit versions of the tool. So I need to remember to take that off. The next thing is, if at all possible, write your test bench in VHDL or Verilog or System Verilog. Don't do a bunch of tickle-based force commands. It's just super slow compared to, writing a test bench in your verification language. If you have any C code in your design that you're bringing in C algorithms, I would say use the DPI versus the FLI PLI and limit that C code as much as possible, because that can be a simulation bottleneck. And then in VHDL, there was never the concept of hierarchical references until VHDL 2008. And so I would say we used to have this thing called Signal Spy, which allowed you to peer down the hierarchy and manipulate internal signals. Use the built-in hierarchical references rather than Signal Spy, because they'll be faster. The next one, set your simulator resolution to as coarse a resolution as you can. So if your simulation is running at, say, 10 megahertz, don't set your simulator resolution to femtoseconds. It's not like it's going to be 1,000 times slower than if you did picoseconds, but it does have some effect on the simulator. So set it as coarse as possible, but then you also need to be aware that if you're using things like the Xilinx DCMs, they require, I think, at least 10 picosecond resolution. So you just need to find that spot where you've got as coarse a resolution as possible, but you're not too coarse and you're getting rounding errors on some of your things. If you ever do gate level simulation, use Verilog gate level representation versus VHDL vital representation. And that is a recommendation across all simulation tools, whether it's Mentor, Kagan Synopsys, whatever. The vital gate level cells were never optimized for performance. So if you have a choice, even if you've done your design in VHDL, your test benches in VHDL, if you have a mixed language simulator, if you need to do a gate level simulation, create a Verilog netlist. It will work. There will be no issues, and it will be way faster than using VHDL vital cells. So the next one is just saying, if you don't have to have the GUI open and you can run in batch mode, your simulation will be a bit faster. It's not a huge difference, but it will be a little bit faster if you can run in batch mode. And then the next one is, of all the things, if you have a choice, do not put your WLF file or your transcript file, which in this case, I changed it from transcript to sim.log. Both of those, if at all possible, make sure they're on a local disk and that local disk is an SSD if at all possible. If your source code is out on a network drive, even if your compiled libraries are out on a network drive, that might slow down the compile a tad. It might slow down the start of your simulation a tad. But once the simulation is running, it doesn't matter that if those things are on a network drive. But if that, especially that model, that vsim.wlf file, if that's being written across the network, that can really bottleneck your simulation performance. So now let's just talk about optimizing the simulation run. So if you have model sim, there is really no optimization you can do, but if you've got at least Questa Core, there is, between the compile and the start of the simulation, there is this optimization step. And what that does is it optimizes the code for performance, and it eliminates redundant signals and things inside the code just to work on simulator performance. So really what that optimization does. So if you're a model sim user, you probably use vlog or vcom to compile your code, and then you do vsim to simulate your code. What Questa does is it has this third step that happens between those called vopt. And what happens during vopt is that it does a lot of global optimizations. So it looks for ways to combine always blocks or processes within your design. If you have 15 processes that are all sensitive to the same clock and reset, it can merge all those into a single process and order the events correctly, that it simulates the same time, but it's no longer now needing to schedule 10, 15 processes, it's scheduling one process. And that can really add up to some massive gains. The other thing that it can do, though, is it can optimize away internal signals that, due to this restructuring of the code, are no longer needed. So you need to plan, if you're debugging a particular block, you need to plan for keeping the visibility of that block available so that you can debug it. So let's look at that vopt a little more closely. So you can continue to do a simulation the same way you always did, where you do your vlog vcom to compile your code, and then you just say vsim. But what's going to happen is, behind the scenes, when you start your simulation, you'll see this message. The first thing that pops up in your transcript will say design is being optimized. And that means that it's running through this optimization step first before it does the elaboration. And so this is good. This two-step flow is good because if you're coming from the model sim world, you don't need to change any of your scripts. You don't really need to do anything. It does take a little bit longer to go from, I said, vsim to, that time zero where the design is loaded up, but you haven't run any simulation yet. And it can be bad for regression runs, because every time you run the simulation, it's going to do a vopt. And maybe you only need to do that vopt once. And so that's where, over here, the three-step flow is where you actually do your vcom vlog. You explicitly run a vopt command, and then you run a vsim on the optimized netlist that comes out of the vopt. So this is good because it's more modular. You have more control over the vopt process, and maybe you don't need to run that vopt every time. So you can save some time on subsequent simulations if you're doing like a regression suite. So what do I mean by preserving that visibility? So if you need to debug your design, you can add a +ACC argument to the vopt command. And what that will do is it will make sure that it preserves every signal inside your design. And so if you need to do debug, you will get it. And so right down here at the bottom, you'll see here I've compiled my test bench, I've compiled my DUT, and then I vsim my test bench. And I put on this extra argument called -vopt_args. And what that means is everything after this equal sign is going to get passed to that vopt command. And what I've done then is said, let's preserve all the signals within the DUT. And so that's just going to be at the DUT level. It's going to make sure it's preserved all of the signals. So that +ACC has a ton of arguments. You can say what level, you can say, do you want to do it recursively down the hierarchy? Do you want to preserve it on a particular entity or on a particular module? So all kinds of commands. I'm going to show you a few versions right here. So right here, I'm going to run the vopt, and there's going to be a bunch more arguments here. But, right here I've said vopt +ACC. I don't agree with this comment. It does not disable all optimization, but it does limit the optimizations that can be done because you're preserving all of the internal signals. Depending on your design, that might be, a 10% effect, or it could be a 2x effect by doing that +ACC. So, what can we do to be a little more strategic? So in this case, I did it again here, and I said vopt +ACC, and I only preserve the nets, registers, and ports. I'm not sure how much different that's going to be from here, but that's design-wise. Here's where it gets kind of interesting. So now what I've said is let's do vopt +ACC, and let's only preserve the signals at the very top level. That may be useful. You make sure you have all the signals at the top, but you might need something a little further down. Here's where I think it gets really interesting. I've got this design, and it's a big design, and at the top level there's 10 blocks, and one of them is this HFTTX, this transmitter. So what I've done here is I've said vopt, and this is the module that I'm making changes to. So this is the thing where I want to preserve all the visibility. So I say vopt +ACC, and then I say the instance name right here is HFTTX, and then this dot says all of its children. So what happens now is when I go to optimize the design, it's going to say, here's this whole design. HFTTX is 10% of the design up here at the top level. I'm going to preserve all of the signals in there and all of its children. That's what this little dot is. But I'm going to let 90% of the design be fully optimized. So I make sure that I've got, visibility for everything in the module that I'm interested in, and I make sure I can do maximum optimization everywhere else in the design. So I might, be 4 times faster than if I just did a +ACC, if I do something like that. Here is another one where I've said vopt, and in this case, I've preserved the registers and the nets, and I've spelled out the actual full instance down to that guy, and I've said, let's just preserve all the registers and nets within that instance. That can be useful, but I think it's a little more useful when you do something like let's preserve the registers and the nets for that instance and 3 levels down the hierarchy from there. So now it at least gives me the ability to debug some of the sub-modules within there. So if you have top level parameters or generics on your design, so maybe you're working on a piece of IP and you can configure maybe data widths or something. When you run vopt, it will lock down those generics by default. So right here, I've got this generic called size, and it's I guess it's on this top/U1. There's a generic called size, and so if I vopt my top level and I output this top opt, then what I want to do is say vsim on top opt, and then I pass this thing to say set this parameter to size 4, and I get this warning saying there's no parameter called size on this, on this module. So what you need to do is either when you do the vopt set the size, and then maybe call this top op underscore size 4, and then simulate on top op underscore size 4, and then maybe I could do it on 16 and 32 or something. This is good as long as that parameter has a limited number of values you want to set it to. But if you've got a parameter and you want to test it from 1 to 1024, you probably don't want to do it this way. You probably want to instead up here say keep that generic floating. So there's an option that says float generic, and then you can do it at the simulation time. So when I run vopt, that optimization that I write out is written into the work library. So you'll see right here, I'm doing a debug flow where I don't know what I need to see. So I say vopt plus ACC. My top level is called top, but I output something called debug ver. So now I could say vsim debug ver and any other arguments, and I'd be running on the debug version. Right here is the regression flow. So don't worry about all these arguments, but basically I've put in the arguments to say that I'm making this thing run as fast as it possibly can. I don't care about debugging. This is just for doing regression, and if I have an error, I can go back and rerun on debug ver. So here I've written opt ver, and then maybe I'm collecting code coverage, so I write out a coverage ver. And then, again, maybe I had some parameters, and so I've set a couple of parameters to different values, and I wrote out a param ver. So all of these things, debug ver, opt ver, coverage ver, param ver, I could say vsim, cov ver, blah, 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 and run a simulation with code coverage. Then I could go back and say, okay, that looks good. Let's run on the opt ver. Let's, vsim opt ver, run a bunch of tests. One of them fails. Then I could say vsim debug ver and rerun that test with my debug. So all of those live in the work library and can be referenced. So when you run the vopt command, that actually locks the work libraries. So be careful, and that's why I say you probably don't want to use that two-step flow when you're doing a whole regression suite. Because let's say I've got, 100 simulations, and it takes about 5 minutes to do the optimization, takes about 10 minutes to run the simulation. If I kick off something and, in the worst case scenario, let's say I have 10 Questa licenses and those all run on a server farm, and I've just submitted a batch of 100 jobs I want to run. Well, if I'm optimizing and doing that two-step flow, and every time it's doing that optimization, then that stalls how many simulations can run at one time, because it's got to wait while that lock is on the library. So if I do the two-step flow, then I do the vsim once, and then I can kick off a bunch of simulations. So this is something that's fairly new. Is we used to have vsim-c, which was command line mode. We've gone to this thing called batch mode, and what that allows you to do, and it's really a Linux thing, and it's by default, when it writes the text log, the transcript file, it uses the standard IO, the standard out utility within Linux. That's not super efficient. So we created a more high performance text writing algorithm within the tool. And so the fastest sim time you'll get is if you say vsim-batch, don't use standard out, and write the log file to whatever. So anyway, that's that's probably your fastest. So another thing that can save you time is using the built-in checkpoint and restore. So checkpoint and restore is a feature of Questa. It is not available in ModelSim, so you need to step up to Questa for it. But what checkpoint and restore does is it allows you to checkpoint your simulation at moments in time, and then at any point you can say vsim-restore that checkpoint, and then reload up that checkpoint and simulate on from there. So this is mainly the easiest use for this is disaster recovery. And it's good if you have a simulation that takes hours or days to run. So, you know, if you've got something that takes 5 days to run, it might not be a bad idea that after every 4 hours of simulation, you can set it to create a checkpoint. And that way, if 3.5 days into a 5-day simulation, you get a lightning strike and the power goes down and your computer shuts down, you can restore back to the last checkpoint and only have to simulate for another 1.5 days versus, you know, restarting your 5-day simulations. So that's the easiest use for checkpoint and restore. The other use for checkpoint and restore takes a little bit of planning, but what you can do, and especially if you have something where, let's say you have a PCI link in your design, and you start your simulation, and the first thing that happens is simulation elaborates, and then the PCI link goes into this training phase. And let's say that training phase takes a half an hour to, you know, negotiate back and forth and, you know, set up the PCI link, and then we're ready to go. And then I run some interesting simulation, and that takes 15 minutes. So it was 30 minutes to get to the link train, 15 minutes of interesting simulation. Now I want to run another test, and it's going to be 30 minutes of PCIe link training, and then 15 minutes of interesting simulation, and again, and again, and again. If I plan a little, I can say, okay, let me restore back to the point that the link has been trained, and then let me have some mechanism that I can go in and say, what test should I run now? And maybe that's, I go in and I force a signal in my test bench that says run this test, or run this test, or run this test, or I read from a file, what test should I simulate? So it just has to be some way of, I restored back to this, you know, the link has been trained, now let's run this, run this, run this. So now instead of, let's say I was going to run 10 tests that each took 45 minutes because 30 minutes of it was link training, that's, you know, 450 minutes. Whereas if I did it the other way, I'd do one 30-minute link train and then 10 tests of 15 minutes each. So that's, you know, 150, 180 minutes versus 450 minutes. So that checkpoint and restore can be used if you have that scenario where there's a common, you know, setup that takes a significant fraction of each of your tests. Then if we go look at vopt, there's something called a pre-optimized design unit within there. So let's look at this scenario. I've got a DUT, which maybe is, you know, it may or may not be gate level, whatever. But in this case, I'm compiling my, you know, my ASIC library, my cell libs, and a few other things. Then I'm compiling my DUT, and then I'm going to do an optimization just on the DUT. And I'm going to flag it that that's a pre-optimized design unit. So now I'm going to output this thing called DUT-opt, which is a pre-optimized DUT. Now I've got a test bench and a test that I want to run. And then I go and I say vsim, blah, blah, blah. I don't do a vopt here. So what that's going to do now is say, okay, here's my test bench. That instantiates my test, and it instantiates a DUT. But you know what? I've got this pre-optimized DUT, so I can just suck that in and then just optimize the test bench and the test. So that's not really good for one test, but if I run another test now, I don't, again, need to do this optimization again. And especially if this is like a gate level DUT that takes 15 minutes to optimize or something, I do this again. I just compile the new test. I rerun my simulation. It optimizes these two things, pulls in the pre-optimized DUT, runs the simulation. So test 3 up to test N. So what that can do is it can save the amount of time where you are doing the optimization, running a simulation, doing the optimization, running a simulation. So now I do the optimization once, and then I just do the simulations. So just a potential place to save more time. This is an interesting thing. I've only actually used this in practice once or twice, but it's kind of interesting. Let's say, again, I've got this simulation, and this is a big design. Maybe it's, 10 or 12 different blocks up there at the top level, and some sub block I identify has an issue, and I need to go fix that. So instead of fixing it, and I don't have a block level test bench for C that's living somewhere in my design, and I keep having to rerun the whole test bench that takes an hour to run. Well, here what I've done is I'm going to run the simulation, and then I'm going to issue this command in my tickle, and I'm going to say VCD dump port. So that's going to dump all the IO of this block C, and it's going to dump it into this file called c.vcd. So I run that once, and then I take block C and I start to do my edits to it and trying to fix it. But instead of going and running my top level simulation, I can just instantiate that sub block, and I can use that VCD file as the stimulus to this block C. So I can just make some changes, run that simulation, make some changes, run that simulation. This runs 10 times faster than the full chip simulation. So, I can just iterate through that until I think I've fixed C, and then I can plug it back into the whole simulation and rerun from the top level. So let's see. This is something only if you're on Linux, and it happens by default now. But it basically, what it is that on the Linux environment, the writing the wave file and the rest of the simulation kernel are actually separate threads. They'll use two different processors to do that task. This has been the default on Linux for about the last 5 or 6 versions. We have not been able to implement it on Windows yet. So this is where, if you have a Linux machine, you can actually see some significant improvement in running debug simulations if you're on Linux versus Windows. So then the question is, do I have an environmental bottleneck? Is there something about my simulation that's slowing down the simulation significantly? And oftentimes what I will do is I'll talk to customers, and they'll say, 2 weeks ago, I'd swear this simulation would run in about 10, 15 minutes. And now it seems to be taking like 2 hours to finish. And I don't know what's going on. I don't know why. And so this is how to debug where your simulation bottlenecks are. So the first thing, if you're going to do this, is you need to get a baseline. And you can get that baseline with this command simstats. So at the end of your simulation, you can say simstats, and it'll print out this thing that says, how much time did it take for this? So this is wall clock time, and how much CPU time. So this is, how much actual CPU time you were running. So once you've got that baseline, now we can use this thing called the profiler. And what the profiler does is it samples, about once every 1,000 simulator steps, maybe it'll say what line of code is being executed at this moment. So now if you run your simulation for a few million clock cycles, you end up getting a profile that says, where is all my simulation time going? And it's about identifying, where the time is going. And I guess, the default is every 60 simulation steps, you will sample what line of code was being executed. So you got to run 10 or 20,000 samples to get some meaningful value out of there. So how do you turn it on? You can do this through the GUI, or you can put it into your scripts that run your thing, and you basically say profile on, and then I forget exactly what this option is. I think it's if the simulator is off running, like C code or something. But anyway, so turn that on, run your simulation, and at the end, save your profile DB. Or if you're running in the GUI, you can just start doing the debug as soon as it's done. So if you've done it in batch mode, then what you do is you say, okay, I've run a batch simulation, it's saved the DB, so now I'm going to fire up Questa and I'm going to open this profile DB and I'm going to analyze what was going on. So here is the analysis. So there's a few different things you can look at, but I'd say either the structural or the call tree are the two things that I tend to look at. And so what you'll see here is it is collecting all the data on what line of code was operating at any one time. And you'll see right now that I've got these two assertion files, and one of them is taking about 74% of the simulation time, and one of them is taking about 18% of the simulation time. So what that tells me is that I created a system Verilog assertion and I improperly set up the trigger in there, and I'm probably firing off that assertion way too often. And it's consuming 74% of my simulation time. And if I go in and I fix that assertion and I knock this down to, 1% or whatever, there's, my simulation will probably run, 30 times faster. So if I do that for these two, this is what you hope to find if you have that situation where you're saying, damn, for some reason this is running like 4 times longer than it used to, is that you screwed something up, you added some code, and you set up the sensitivity lists incorrectly so that this code is firing off all the time. And so if you fix those two things, you'll probably see a huge jump in your simulation performance. So that's the kind of thing that you hope to see in your profiler. So that's just one of the other views, the ranked view. So that profile database is a binary format. Again, you probably don't need to worry about this because we're pretty much shifting to 64-bit versions of things. And there we go. So at this point, we've talked about, the simulator performance, but let's think about that. So in 2010, we did one of these Wilson research studies, and you'll see these like in the IEEE Times, but we asked a bunch of verification engineers, where do they spend their time? And so if you look at this, we gave them a few categories, and they said they probably spend about a quarter of their time developing their test bench. They spend about a quarter of their time like waiting around for the simulations to run. And then they spend about a third of their time debugging errors that they find. And then I don't know what they do. They spend 14% of their time hanging out, talking about what they did this weekend. So we did this study again in 2014, and we were a little more granular in what we asked. So instead of just test bench development, we broke that up into like test bench planning and then test bench development, running simulations. So if you look at this now, the creating the test bench was about a third of the time. Waiting for simulations to run has actually gone down to about 20% of the time, and the time spent debugging has gone from 32% to 44%. So we're seeing that it's that debug time is the thing that's really causes is the biggest delay. So even if we made our simulator run twice as fast, we might cut down this time, but this is not the long pull. It's if we can make the debug faster is where we can really save some time. And so that kind of goes back to this quote, everybody says they want a faster simulator, but if I asked them what they really wanted, Henry Ford said they would have said they needed faster horses, but instead he introduced the automobile and changed the game. So one of the things that we've done is we've said we're working on a faster simulator for you, but we've also come up with a better way to do debug, and that is with our Visualizer debug environment. So this is our next generation debugger. It is different from the standard debugger that comes with ModelSim and Questa. It's built for much higher capacity and much higher performance. It is more intuitive and easy to use. I mean, I have to say I like the traditional Tickle debugger that comes with Questa, but I actually have started to use Visualizer, and I find things that take me 7 or 8 mouse clicks in the traditional debugger take me 1 or 2 mouse clicks, and everything is much more automated and synchronized. So it just makes the whole debug process faster. And if you're doing System Verilog UVM test bench, I would say the UVM debug abilities are much, much better in Visualizer. So what is Visualizer? It is built on a new technology. I mean, the Questa debugger, the Tickle debugger, is pretty much built on the same foundations that the debugger was built on way back in 1983 when ModelSim first hit the market. So, we've improved it, and we've modified it and modernized it as much as possible, but at some point it is, a 2 decades old debugger technology, and there's only so far we can go with that. So Visualizer is our next gen debug environment. It is an add-on debugger, so it is purchased on top of the debugger or on top of the simulator, but it is so much faster and so much better that we find that it's really, worth it to look into. So as I already said, it's built on new technology. It's much more intuitive and synchronized between everything. We can handle way higher capacity designs. I don't know if you've ever seen when you're in the traditional Tickle debugger that you've got a whole bunch of signals and a whole bunch of time, and you go and you zoom out on the wave window and you see those waves like crawl across the screen. And it probably only takes about 10 seconds, but it feels like it's about 10 minutes because it takes so damn long. There's none of those issues with Visualizer. So UVM simulation much more efficient. So one of the things about Visualizer that makes it, you know, and the debug on it is impressive. But another thing is, we no longer, in the previous section I talked about using that plus ACC argument to preserve visibility. And here's the impact of that. So if this light blue is, if I ran a simulation in regression mode, where I don't care about preserving any signals, all I'm doing is running and getting a pass-fail. Let's say that would take 10 minutes normally. Now, just putting that plus ACC switch, because I've got a debug and I don't know what I need, so I put that plus ACC switch on, and that 10 minutes will go to about 20 minutes, just putting on that plus ACC switch. And then now I say, well, you know what? I'm just going to save every signal in the design because I don't know what I need. So then that'll take it from 20 minutes up to about, you know, maybe 70 minutes. So we can see there's like a 7x impact from doing a full regression simulation run to a full debug, collecting all the waves. So that's with the traditional WLF. With the new Visualizer database, setting the -debug switch that says I'm going to be debugging this has virtually no effect. So I go from 10 minutes to maybe 11 minutes. And then if I say, okay, I want to collect every signal in the design, it'll go from 11 minutes to maybe 20 minutes. So you'll see the comparison there is that we're about 3 times faster, 3.5 times faster, doing a full signal debug versus the Questa debug. And here's a couple of examples. So, you know, you'll see this one, full optimization is the same for both of them, doing it with the WLF, doing it with the Q wave for Visualizer, and you'll see, you know, for most of them, we get about a 2.5x speed up. Some designs, we don't get quite that much. So in this case, it was only about 1.5 times faster, but we've seen designs where it's 4x or more. So average somewhere around 2.5 times faster. So let's take a little look at Visualizer. A couple of things that are really nice is that the source code window is completely synchronized with the design hierarchy window. So any place you click on in the design hierarchy, it automatically displays that source code. And so you can quickly, you know, click on different places within there and see that. And then, you know, if you click on any signal in the design, you can say, you know, trace me to all the receivers of that design, or trace back to the driver of this signal. So that's super quick, and it's 1 click versus 3 or 4 to do that in the traditional debugger. Everything is synced to the active cursor. So as I move that active cursor around, any annotation is automatically updated. Something that's really unique to Visualizer is this view called the time cone view. And that is, I've got this signal, let's say interrupt right here. And let's say it went to an X in my simulator. If I was to trace that back in the traditional debugger, it would trace back, and you'll see these are flip-flops. And it would say, okay, here's this X, and it would go back. And then at some point, as I'm tracing back, these signals might not be X anymore because they're sequential and they're, you know, later in time. But this time cone view is time aware. So it knows that this is a flip-flop. So when it does this annotation, it says, when I go through this flip-flop, I'm going to show the data here as a cycle earlier than the data over here in red. And then everything in yellow is, you know, a cycle earlier than here. And, you know, I can keep debugging back. And so I get to look back through sequential logic, but view it all as what caused this to go to X. And so it's a much more efficient way to debug back through your data path, because it is aware of all the sequential logic. And for some reason, this slide doesn't show up, but there's little lines here that says, you know, what clock each of these data points was coming from. There's this thing called biometric searches, which, you know, if you're looking for certain values, and this is especially, you know, good for, like, you have a data path and you want to trace, you know, some value that came in. And so you say, okay, here, this data path came in as 0 EEE. And so I can kind of trace every place that that value shows up, and it'll highlight it with whatever color you tell it to. And so, you know, now I can kind of see, here's what this came in. It went through, you know, some logic, and I can zoom out. And even from all the way zoomed out where I can't read the values, I can kind of trace where that purple is going through my data path. So that's kind of an interesting thing. So this is just talking about, you know, especially once you get into System Verilog and UVM, debugging test bench stuff can be difficult because System Verilog test benches are dynamic and they're class-based, and, you know, there's a lot of things built in to Visualizer to help you debug System Verilog test benches. So you get a schematic viewer of the test bench structure, and if it changes over time, that'll be reflected in this view. You have full class debug, so you can debug down through classes. You can put classes into the wave window, so you can see all of that information in the wave window, which is, you know, not all debuggers are able to deal with those dynamic classes. There's a stream viewer within the Visualizer debugger, so I can look at, you know, what data packets have been sent through my design, and it kind of shows, you know, a stream of these are the packets that went through, what time were they generated, what was the different arguments on them. You can trace by packet ID, you can trace by a lot of different things. You get a view into the UVM factory so that you can see all the parameters and all the overrides and all the data within the UVM database. So the configuration database, you can say, okay, what's in the configuration database? It can help you in writing your test bench and making sure that you actually wrote the right thing into the database so that other things that are grabbing it are seen, and you're actually getting the right configuration into your UVM agents. That's probably as deep as I want to go into UVM. And so the kind of the summary is that Visualizer is our next generation high capacity debugger. Over the next couple of years, we're probably going to be replacing the old Tcl-based debugger with a version of this Visualizer debugger. So we're going to have kind of a cut down basic version that you get with the simulator that has a lot of these benefits, but probably the things like class debugging and you know, some of the the super advanced functions of Visualizer won't be in that cut down version, and that's something that'll probably be coming in over the next couple of years. So this is definitely the direction that our debugger is heading, but Visualizer is kind of the full-blown debugger with all the features currently. It, as I say, is our next generation debugger. We are continuing to make sure that we have the performance, capacity, and ease of use in our debug solutions, which, as I showed in those earlier slides, debug is probably the biggest task for any verification engineer. So that's pretty much what I had for today.